this situation in the assignment. It's similar, but it deals with output tasks. Right, so what we do now is we start talking about the standard template library, which was adopted as a library for C++ language. It was designed in 1994 by two people from Hewlett-Packard, Alexander Stepanov and some lady. And the way they design it did not follow much the object-oriented approach, because they separated data, which come into containers, and functionality. Functionality are implemented by algorithm. While in object-oriented programming, you know, we design types where we put together data and functionality. For efficiency reasons, they decided, when they came up with this standard template library, to separate data and algorithm. And the link between them is a concept, iterators. You will see that the iterators in general are not classes, but it's a concept, a type of types. So containers and algorithm work together. It's a very powerful mechanism, because you have one algorithm, sorting, for example, and it works on vectors, it works on double-ended queue, it works on arrays. You have a single function, and can work on all these different types of data. It was a very, very interesting approach. So there is a lot of work in this area, standard template library. And I have read that standard 14 is out. Standard 17 is published. Very few compilers abide to them. And they are working on standard 20. C++ 20, C++ will have a new standard coming out in 2020, and most changes will be in the template, standard template library. It will introduce new things. So, today we will talk about data types. And in the library, the data types are containers. Containers meaning collection of objects of the same type. The string is a container itself, because it's a collection of individual characters. The string somehow is the simplest container you can have from explanation point of view. From our point of view, we are looking at these three groups of containers: sequence, associative, and container adapters. I have updated the slides last evening. I discovered that the company SGI, it was Silicon Graphic something, which used to have a very good documentation for STL, decided to remove it. So this link, you can go there and go to the bottom. A person, this company has decided to remove information about STL because they say it's outdated what they have there. But for information point of view, you can, for what we are using, that documentation was very good. At the bottom of that page, you will see a link to a person who downloaded all the documentation in the past, and he makes it available. So you can still go there and have a look. But other than that, these two links are active and up to date. And there is a book of, roughly speaking, 1,000 pages. Nikolai Josuto's The C++ Standard Library, which was published a while ago, and he has updates on his website. But he has a lot of code examples. If you ever need to go into more details, please try to have a look at his explanations. So, C++ standard has adopted this STL as a library for C++ language, and it comes with a number of classes, and with every standard new classes are added. We are concentrating on a subset where there are many other classes we are not touching in the STL, but the main classes we are talking gives you a lot of tools. This is not only an important part of C++, but it shows you how to build a good library. The problem is you have to work hard to go and get a hold of the code provided for vector, for example. The code, the source file are not available. In some books, you have snippets of those approaches. And if you search the internet, you can find some examples, but unfortunately, they didn't make public the code source files for their tools. All we have is some good documentation, which tells you that there was a lot of thought included in the design of these tools. In order to use it, you have to know what is available and what are the performances, what are the conditions you have to follow when you use it. As you know, object-oriented means whatever is underneath can be changed. How the vector is implemented, it can be a linked list of nodes, it can be a tree, it can be a double linked list. We don't know and we don't care. It can be changed anytime. All we have to know is what method are there, what are the parameters, and what are the ways to use the vector. So, good example refer to the fact that there are very good performances explained in the documentation. CPP reference gives this performance features. As I said, there are three big parts. There are more, but we are concentrating on these three big parts: containers, iterators, and algorithms. And the iterators is a linking part between these two groups. Outside this, we have function objects and many other facilities, in particular for concurrent programming and multi-threading, which is an area C++ entered with C11. So as you can see, algorithms use iterators to interact with containers. We will talk about that. Today we talk about containers, tomorrow we talk about iterators, and next week we talk about algorithms. After that we talk about smart pointers, and this is it about C++. So last lecture next week we'll start talking about Java. As I said, containers are collection of objects of the same type. And in principle, we have containers where you can rely on the element being arranged one after the other. So sequence containers, you have one element, and then with plus plus you go to the next element, and plus plus to the next element. So there are no holes, kind of. Associative containers are a little bit different. They are organized not in a linear way like sequence containers. Linear way means this kind of, no matter that you have pointers or not, you can think of sequence containers like this: one element, another element, another element. For vectors you have something like this, okay? For lists, double-ended queue, you have here pointers, 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 but you have element after the other. Now for associative containers you have trees, normally binary trees, like this. Data is kept in a structure like that, where you have each node has two children. So it's not a linear structure. And the way they design it like this is very good for searching, finding data, because you will see for associative containers, data is kept in sorted order. And therefore, searching is very fast. While for this, if you want to search for an element, if this is not sorted, you spend a lot of time in order to finding one element there. So different container was designed with different goals of efficiency in mind. In terms of sequence container, we will look at vector list and double-ended queue. So, as you can see here, sequence means elements stored in one after the other. Of course, the first one doesn't have anything in front, and the last one doesn't have anything after it. But other than that, each element has a predecessor and a next element. And these are the three main containers we are talking about. So, the most versatile is the vector. It's, if you want, a very smart array, very smart. Because a vector is designed with a class, and it knows a lot of information about itself. How many elements are there? It's a method in the vector class. What is its first element? What is the last element? So, if you look at a vector, you can think of it like being a sequence of one element after the other. What you can do to work with that, pop back means remove the last element. Back refers to the last element. So as you can see, if this is V, pop back doesn't take any argument and removes 13, which is returned by the thing, by the method. V pushback adds this argument to the vector at the end. The best efficiency, the best performance you get when working with a vector is to work with the end of the vector. Removing elements from end and adding at the end gives you the best performance. Removing element from the front or putting element at the front or in the middle doesn't give you a very good performance. Because if you want to add an element here, you have to do a lot of work. You have to shift these elements, so you make space for this. And there are one possible problem if you haven't got enough space allocated. Because anytime when you declare a vector object, it comes equipped with a specific amount of storage. And you can push back elements, and you can fill that storage. If you push another element which exceeds the allocated storage, what the vector does behind the scene is that looks in the memory for a new space. This is done automatically. You don't have to do anything. The vector does this. So if we have this memory allocation, we have filled in, and we want to add a new element in the middle or whatever, the system looks at the memory and finds enough space to allocate extra. Normally the vector doubles the space when you add new elements to make it a little bit more efficiency, so you don't reallocate any time you add a new element. So normally it looks, okay, I have 2, 4, 6 elements here. I want to add the 7th. I will look for 14 consecutive spaces. And it looks for 14 consecutive spaces. Let's assume that they have 40, and then copies for us each element here, right? And then release this memory. What happens, everything is fine, you can work with this thing very well because it has enough memory, it is in good shape. It takes time, right? It takes time to go from here and here, so this is not the main issue. The main issue is invalidation of iterators. When you do this, if in your code have used an iterator, like for example, find element 5, you find the element with a method which returns an iterator to this location. And after you find that element, you decide to add some elements to the vector. And after you add those elements, you want to use that element position you have found. That iterator. Iterator is like, for the moment, a pointer in our case. Now, your iterator was pointing here, but 5 now is here. So this iterator is invalidated. It's dead. It's not working. So this is one issue with vectors. And you will have an exercise in a tutorial. But this can occur seldom. It has to be quite convoluted, as you see. You have to look for this element in the initial vector and then perform some additions, and the vector was moved here, but you still want to get hold of this initial location. It happens. We don't go into details, but these kind of bits and pieces are spread all over the standard template library. So you have to read and try to understand how the data are implemented and how the methods work a little bit, reading the documentation in order to avoid problems. Right, so the best way to work with vectors is through the end, the most efficiency. You can see that you can construct a vector from a C array very easily. You have, in order to get all these elements in your V, specify the beginning. Array is the same with reference to array 0, probably you know. Array plus 5 refers to this. And it copies everything. Now, because vector is implemented with a template, remember, you always, whenever you use vector, you have to include vector header, include vector, and then for every variable you declare, you make sure that you specify the type. This is a must for all containers. Now, you will see that the vectors come with index notation, like in array. You can access v3. Also, you can access with methods vector. Comes with begin method, which gives you access to this element, and end. The end points to the location after the last meaningful element. So be aware, the end points here. The begin and the end return pointers, iterators, we say. Be aware, the begin is a pointer. The end is a pointer. To get access to 12, you dereference. So you dereference the begin. You never dereference the end because there is no element there. But this was a choice of the designers of the library to check for emptiness. An empty vector has the begin equal to the end. Yeah? So if we have no element there, means that the beginning and the end are the same and there is nothing there. So this is one thing. An example, vector using namespace, create a vector of integers, and you will see the vector comes with a lot of constructors. We are invoking here the default constructor. We don't pass any argument. We are invoking the default constructor. We can invoke a constructor which takes a C array, as you can see. So if you look at the vector class, and this is the way most containers are defined. They take as parameters, they take 2 parameters depending on the container. For vector we have 2, the type of the element and the allocated model. Now this is by default provided. It can be changed if you need it, but we don't go there. So T, for compatibility reasons with C++ before 11, class is used, and here you have a lot of description, but then constructor for vector. We have, if we go to C11, as you can see, default constructor, a constructor which takes just a number of elements, and explicit means do not convert an integer to a vector. So explicit keywords prevent implicit conversion, which is provided by some constructors I mentioned at some stage. So whenever you see explicit, means implicit conversion is disallowed. And then you can have another constructor which says how many elements in the vector and what is the initial value. Then we have this constructor which allocates for CRA, input iterator, we will see, and first and last, it doesn't matter. We can construct a vector from another vector. What is this method called? You should know, because we talked about this. Constant reference to a vector. This is? Copy constructor, exactly. This is a copy constructor we talked about for classes. Right, and then some other copy constructor where the method of storage is changed. What is this? What type of constructor is this? We also talked about. Move constructor, that's right, move constructor. Another form of move constructor where the storage is defined by something else, we don't know. And then initializer list, we are not talking about this, but this is an addition introduced by another type of lists introduced by C++11. This allows you to design vector and assign values straight away, like vector int v equals curly bracket 1, 2, 3 curly bracket. This is an initializer list, and this is possible for vectors because of this constructor. So if you design a type and you want to use for your type initializer list, be aware you can't do it at the moment. If you design a type, let's say my tree, and I want to use initializer list for the tree type, you have to implement an initializer list constructor parameter. But we are not covering this. This is an advanced topic. Right, so as you can see, we have a lot of constructors, and then you have explanations here and various examples, but this, after that, you have a list of member functions, and this is something you probably should have a look at. This one tells you that there are some predefined type, value type, which is just a name for template parameter T. Allocated type, we don't think about. Reference, it's it's a synonym for this constant pointer or deals with thing. Iterator, we will talk about this. Random access thing. And as you can see, iterators come in this form: iterator, constant iterator, reverse iterator, constant reverse iterator. Just have a look. We will mention it tomorrow. But I read that with C++17, they will make iterator obsolete because it's a little bit confusing. It's good to know they will stay in the language because it was part of the language and because of compatibility with the previous versions, but the importance of this will diminish. Size type is unsigned integer, remember? Type def for unsigned integer. This is a size type, and it's all used for dealing with number of elements in the vector. And then we have this begin, return iterator to beginning. Front is a different thing. Access first element. These are all public member functions. So this returns an iterator, and you have to dereference. Front returns the element itself. So there are these methods for the vector, how to change them, and how to access elements. Index operator is like the arrays. At, it's like this with bounds checking. like in string. Okay. Front, back, and data is a method introduced in C++ 11 to accommodate for more types of data. And then insert element, one more element at a specific location, which is something like this. You want to insert here 5 elements, and then the function has to deal with, the vector has to deal with this insertion. Now erase elements. If you want to erase one or more elements, the vector deals like this, with erasing like this. This is overridden by the next element, the next element. So what the vector says, my size, it was 5, I erase, it was 2, 4, 5, yes, 6, let's say. It was 6, I erase 5, my size now is 5. I am up to here. But you will see this memory is not returned to the system. You can still access this somehow, and it's a waste of time to return this to the system. As long as you keep, with the specification, after erasing one element, you have the vector with size -1, and you work with that element, you are fine. You don't have to go and do the other thing. Clear does the return of memory to the system. So for vector, when you erase memory, which is not used, is not returned to the system. The double-ended queue does returning memory. So when memory is an issue between vector and that double-ended queue, preferred would be double-ended queue. Push back, pop back, we have talked about. Notice that there is no push front, pop front. There is none, right? Because removing the first element is the most inefficient thing in a vector. You have to move all this there. Right. Of course, you can use erase the first element, but this somehow tells you that maybe you are using the wrong container if you need to do a lot of erasing from the front. Okay. So if you click on this, you get more information if you need details about the vector. And here we have an example of using very simple, as I said, pushback is the best method to use for the vector. Avoid using, with this for loop, you can say VI assign random, right? It's the same somehow. V0 is assigned the first element, V1 is assigned the next, V0, when I is 0, V1, V2. Now, index operator does not handle adding elements very well. Some compilers will complain. They don't allow you to use, after you have declared V like this default constructor, and you use VI gets this value. Some compilers tells you it's difficult to do this, or it's an error, does not allow you to use index operator. The best way is to use pushback, because this method deals with memory allocation when we are pushing back more elements than it was allocated at the beginning. Now, as I said, a vector comes with a lot of information about itself. It knows how many elements are there, v size. This will be size type or unsigned int if you get a warning, because size returns size underscore t or size type, or just plain unsigned int if you have a problem. And then we go with a for loop and display the data. Of course, we can go with for ranges, and we will see some other things. So what we get will be the random values which were assigned there. The double-ended queue is another smart container vector, and double-ended queue are the most powerful containers in the standard template library. After that, all other containers are a little bit less powerful. Because they can't have random access. In a linked list, to go to the third element, you can't jump straight to the third. This is random access. In a vector, you say, oh, I want the third element, give me A3, and you jump straight there. But in a list, you have to start with the first element, go to the next, till you get to the third element, right? So no random access for lists. Yes?
Why would we use vector instead of DQ?
Why?
Why would we use vector instead of DQ? I mean, DQ seems more versatile because you can use it in both directions, and vector is just for
Everything which comes with more features, you pay a price for it, right? So with double-ended queue, you can work at the beginning and at the end, but some methods are slower. When you run, for example, sorting or something like that, the method is slower as when you use the vector. Erase is one example. In the vector, memory is not returned to the system. In the double-ended queue, memory is returned to the system after erasing. This is an extra step. It depends. If you have just one element integer, returning a memory location for an int, it's easy, it's fast. But if you have elements of type array, or of 10 or 100 elements, you can have element which is an array itself. Returning the memory for 100 elements is much more time consuming than not returning it. So when you have more features, vector, double-ended queue, some methods have lower performance than when you have lists, for example. To remove an element in a list is very quick. Oops, I want to remove this. Oh, we destroy the link. And this is it. Very, very quick. All we do, we set a place here, and then we destroy this link and move it to point here, and then we return this to the system. So now we have it's constant time removing an element. But to remove an element in a vector, it's linear time. If you want to remove the fourth element, right, you have to move whatever elements are after it. And this, as I said, takes time. And for adding, it can be even more time consuming depending on if it needs allocation or not. So be aware, each container is designed to perform very well specific things. And it's good to know what are they good at and use them. We have a little bit of discussion at the end for use a proper container for the task at hand. At our level, probably the vector and the list will be enough for the moment. You can't learn everything in one go, but it's good to know what is there and what are the small differences, the main differences, sorry, the main differences, not the details. So double-ended Q is the abbreviation, as you can see, and it's a dynamic array. And it's designed to perform well with working at the beginning and at the end of the queue. But again, they are linearly stored. As you can see, working at the ends is fast. Inserting in the middle, it's slow. To work with double-ended queue, you include the proper file, and as you can see, the declaration is very similar as for vector. Very similar. This is the name of the type. You have to specify the type of the element. Now here we put elements at the front because we can, and then this code is exactly like the previous one. So size is provided by most containers, and then with a index operator, so double-ended queue provide the index operator, push back, push front, provide at operator, like the vector. You can access individual elements. Right. I prefer, and I recommend you to use this approach. You will see a lot of examples. Sometimes I forget myself, and I put I less than D size. I can say for, I can skip this. And I can say for integer I, 0, I less than D size, increase I, display DI. If you go through this for loop 5 times, it doesn't matter that you put like this or put this size here straight. But if you go through the array, through the for loop 10,000 times, be aware you invoke this function 10,000 times. 10,000 times. This is time consuming, slowing down the program, not very efficient. So try to get used to this approach. Do not put this size here because you invoke it. After each iteration, call the function. This is one minor thing which relates to style. The list in C++ in STL is implemented with a double linked list. Probably you know this is something like that. You have a front, and then each element points to the next and then to the end, kind of end or null or something like that. So except the first and last, this is a head and this is an end. Each node points to the previous one and to the following one. Now, these sequences do not provide random access. We don't have index operator or at operator. So be aware, whenever we have this list, or we will see other sets and sets, which is a different story. They are designed for inserting and removing from the middle. Of course, front and back are also very, very efficient inserting front or back. But compared to what we talked before, deck and vector, lists behave very quick to inserting in the middle. Constant time, the most efficient you can have. Include list declare the variable, and you have pushback, like for the vector, if you want to construct your list. It comes with empty method, and normally you do something like this in a while loop, or whatever other iteration you want, as long as you have elements in the list, not empty. Display the element, access it, but it's still there, and now remove it. So pop front takes the element out. Takes the element out. Right. So, in terms of these sequence containers we have talked, they are similar because they are organized in linear fashion. You have empty, max size, the largest number of elements you can store there before a reallocation is done. How to swap, so you can swap vectors, lists, deletes all elements of the container. Assignment operator, which makes copying, deep copying, assignment operator. Test for equality, test for difference. They are not the same. Equal means the same elements, the same size, and so on and so forth. So these are common to all the containers we have talked about. And then push back, pop back, all have it. Erase, where from, and then inserting where and what, where, how many, and what elements. So start from this location and insert an element. So you can work with individual or sub-individual. And we stop here and continue tomorrow when we will start with this 5 minutes talk by Strauss.